How does the hot reservoir affect coefficient of performance? Have you ever wondered how the temperature of a hot reservoir impacts the efficiency of heating and cooling systems? Let's break it down in a simple way. The coefficient of performance, often referred to as COP, is a key measure of how well heat pumps and refrigerators work. It tells us how much heat is moved compared to the work input needed to do that. For heat pumps, which transfer heat to a hot reservoir, the COP is calculated by dividing the heat delivered to that hot reservoir by the work input. On the other hand, for refrigerators or air conditioners, which remove heat from a cold reservoir, the COP is the heat taken from the cold reservoir divided by the work input. Now, the temperature of the hot reservoir, usually noted as TH, is very important. It directly affects the maximum theoretical COP, known as the Carnot COP. This maximum COP is based on the absolute temperatures of both the hot reservoir and the cold reservoir, which is noted as TC. When we look at the formula for the Carnot COP for heating, it shows that as the temperature of the hot reservoir increases, the numerator in the equation increases. This might seem like it would increase the COP. However, the denominator is the difference between the hot reservoir temperature and the cold reservoir temperature. If TH goes up while TC stays the same, that difference increases, which can actually lower the COP. To put it simply, a higher temperature for the hot reservoir often means the system has to work harder to transfer heat to a hotter environment. This can lead to a lower COP. For example, if you are trying to heat a space to a very high temperature while the outside is much colder, the heat pump will need more work input. This results in a decrease in efficiency and a lower COP. For cooling systems, the hot reservoir is where heat is expelled. If the temperature of this hot reservoir rises, it becomes more difficult to reject heat, which also decreases the COP for cooling. In summary, as the temperature of the hot reservoir increases, the coefficient of performance generally decreases for both heating and cooling systems. The system must overcome a larger temperature difference, which means it requires more work input. The COP is at its best when the temperatures of the hot and cold reservoirs are close together, minimizing the work needed. Understanding how the hot reservoir affects the coefficient of performance can help in designing and operating heating and cooling systems more effectively. By managing the temperatures of these reservoirs, we can improve efficiency and performance in thermodynamic systems.